Good morning everyone. I will be handling a course on numerical analysis, and this course consists of say about 45 lectures, and numerical analysis is a branch of mathematics that is concerned with the theoretical foundations of numerical algorithms for the solution of problems that arise in scientific applications. It actually covers the mathematics and the methodologies that underlie the techniques for solving scientific problems. For example, if one wants to compute what sine 25 degrees is and he wants to use his calculator, then he just presses some buttons on the calculator, and then at the end he is able to arrive at the value of sine 25. Does the calculator have a knowledge of how to compute sine 25 degrees? Actually, the calculators are programmed to implement certain numerical techniques with the help of which one is able to arrive at the value of sine 25. So, the computers are programmed to implement the numerical techniques that we develop in this course on numerical analysis. Suppose say one tells you that he uses a computer to design an aircraft, is able to predict the weather, or he is able to solve complex problems in science or engineering, then he actually uses this computer to implement certain numerical algorithms which he knows to solve these complex problems in science or engineering. Therefore, in this course we would focus on the development of such numerical algorithms and then try to solve some simple problems with the help of these numerical techniques, and we focus our attention on the following three issues. Namely, we shall be concerned with how accurate our numerical algorithm is, what is the amount of error that is incurred at each step of scientific computation, can we control the error that is incurred, or how to control this error that is incurred at each step of computation. And secondly, we will focus on the efficiency of the numerical algorithm that we have developed. And thirdly, we will also see is the method that is developed is a stable method. If small deviations are given to the input to the computer, whether the outputs have large deviations. If this happens, then we say that the method is an unstable method, or corresponding to small deviations in the input, the deviations in the output are also small, then we say that the method is a stable method. So, our goal would be in this course to solve certain set of problems that arise in scientific applications, and to solve these problems we require certain techniques which are numerical techniques. So, develop these numerical techniques or algorithms and implement them in solving our problems. So, we will illustrate each of these techniques or the use of each of these techniques by solving some simple problems, keeping in mind that we should be very careful about how accurate our solution is, how efficient our method is, and is the method stable. So, numerical mathematics does not require a large amount of background, but it does require a good knowledge about the background. So, we shall start with some basic tools of calculus, the mathematical preliminaries, and then start dealing with the topics that we would like to understand. So, in fact, in this course we will be focusing our attention on about 5 important topics. The first topic being interpolation. So, let us see what is interpolation. Suppose say you have some information about a function at a set of say n plus 1 points, namely x naught, f of x naught, x1, f of x1 and so on, xn, f of xn. So, you are given n plus 1 points and the corresponding values of the function. So, x is an independent variable and f of x is a dependent variable depending on x, whose values are known at a set of n plus 1 discrete points. I would like to reconstruct the function f of x by seeking a polynomial p n of x of degree at most n, such that this takes the value at xi f of xi for I is equal to 0, 1, 2, 3 up to n. Or in other words, I would like to get a smooth continuous curve, namely a polynomial p n of x of degree at most n that passes through the points xi comma f of xi in the xy plane. So, if I do that, then I have reconstructed this function f of x, which takes these values at a set of discrete points. Or one may also come across the following situation, namely I know the function f of x say in some closed interval a b, a continuous function in the closed interval a b, all of whose values are known to me. I am interested in approximating this function f of x by means of a polynomial p n of x of say degree n in this interval a b. Then I would seek the polynomial p n of x of degree n such that p n takes the value f of xi for I is equal to 0, 1, 2, 3 up to n. So, if I seek or if I determine such an approximation to the function f of x by means of a polynomial p n of x such that p n passes through the points xi and p n takes the value f of xi at the point xi, then I have a polynomial that approximates this continuous function f of x in the interval a b, whose values are all known to me in the entire interval a b. When I do any of these, right, either problem 1 or problem 2 and seek a polynomial p n of x that interpolates the function f of x at a set of given discrete points, then I am essentially doing, right, interpolation by polynomial. So, for example, say if I am given information about rainfall in every 2 years or the sales of certain commodity in every 2 years, say starting from 1998, 2000, etc. up to 2000, say 16. So, I know in these years what is the sales of a certain commodity. Say it is some 10 lakhs, this becomes 12 lakhs and so on. So, it has increased by say, right, 72.5 lakhs in these years. One may be interested to know, although the information is available, one has no information about say what happens in the year 2015. The information given here is in the year 2014, but one has no information in the year 2015. But for some practical purposes, one may require the value or the amount of sales in the year 2015, right. Then one can fit a polynomial Pn of x, right. So, this will be x and this will be the value of f at that x which are given to you. So, one can find an interpolating polynomial that interpolates this data and obtain a polynomial of the form say a naught plus a1x plus etc. plus a n x to the power of n for any x that lies between 1998 and 2016. So, one will be able to immediately obtain the missing information in the given data. So, the polynomial interpolation helps you to get the value of the function at any point x within that interval. So, we will be trying to get algorithms for the construction of such polynomials which are known as interpolation polynomials that interpolate the function at a given set of points. While doing this, we do incur some error. For example, if f of x is equal to say e to the power of x in some interval 1 to 2 and we are approximating this function by a polynomial say Pn of x in the interval 1 to 2. As a result, we would incur an error given by the difference between f of x and Pn of x. So, we should be able to see what is the bound on the error, namely absolute value of the difference between the two, and see whether it can be made less than some quantity at any x which is in 1 to 2. So, that we will be concerned with the accuracy of the approximation that we have made using this polynomial interpolation. Next question is, what happens if the points are equally spaced or if the points are arbitrarily located. So, we should be in a position to construct polynomials depending upon what the given data is. So, we shall look into all these aspects while constructing interpolation polynomials. So, that would be the first topic that we would focus on in this course. Now, once we have constructed an interpolation polynomial, the natural question that comes to our mind is, okay, I am given a set of information like this, will I be able to get some information about the derivative of this function at any x which lies between x naught and xn? That is a question. Or the second derivative, the higher order derivatives, will I be able to get some information about the derivatives? Right. For example, if one writes down say the distances covered by an automobile at some intervals of time, I would like to know at what speed at which this vehicle has moved between this time and this time, which means I require the information about the derivative of the function values which are given to me, namely the velocity being the rate of change of displacement or the rate of change of distance that is travelled. So, there are problems in which we require the approximation of the derivatives of certain functions whose values are prescribed in the form of discrete data. So, how are we going to approximate the derivatives when we have the function value specified in the form of a discrete data? So, these aspects will be covered in numerical differentiation. You may be given an integral of the form integral a to b f of x dx, and this function f of x may be a complicated function, or the definite integral may be such that you will not be able to apply any of the techniques that you already know to evaluate this integral. So, in that case we should be able to get a value of this integral, and we do this right in numerical integration. As I said earlier, because we are integrating and evaluating it numerically, there would be some amount of error that we would have incurred. So, we do take care of the accuracy in evaluating this integral numerically, and we would also focus on the computation of what the error is and how to control this error. Can we get better and better methods so that the error can be made as small as we please? So, these aspects will be covered in numerical differentiation and integration. Then we move on to problems where we will discuss about the solution of either transcendental or algebraic equations of the form f of x is equal to 0. And we all know that if f of x is a linear equation of the form a plus bx is equal to 0, if suppose f of x is a quadratic equation a plus ax square plus bx plus c equal to 0, then you know that this equation possesses two roots given by minus b plus or minus root of b square minus 4ac divided by 2a involving radicals. So, you will be able to solve a quadratic equation, and it is known that a cubic equation, fourth degree equation, which is called a quartic equation, these equations in general can be solved and the solution can be given in terms of the radicals under certain conditions. So, one tends to think that it may be possible to solve equations of this form. Say, if we restrict even to integer coefficients, it may be possible to solve, for example, a fifth degree equation of the form, say 4x to the power of 5 minus 2x minus 7 equal to 0. In terms of the radicals, no, the answer is no. One will not be able to get a solution, right, of a fifth degree equation of this form in terms of the radicals, and in general it is not possible to write down the solution in terms of such radicals, right, in the case of equations whose degree is greater than or equal to 5. And these are algebraic equations, but we may come across equations which involve transcendental functions like log x, e power x, etc., the trigonometric functions, the exponential functions and so on in f of x. Then solving these equations analytically is a formidable task, it is a difficult one. So, one has to seek the techniques or numerical methods for solving such equations numerically. So, we will be focusing on the techniques which are both direct as well as iterative techniques for solving these equations. And as I said, we would perform a thorough analysis of the error. If we do an iterative technique, then we will be generating successive iterates for the roots of this equation f of x is equal to 0. So, we would like to see as the number of iterations increase, whether the sequence of iterates that we have generated for the roots of this equation, do they converge to the solution correct to the desired degree of accuracy that we want. All these things will be dealt with in the topic on solution of algebraic and transcendental equations. We will also focus our attention on the solution of matrix equations. Solution of matrix equations of the form Ax is equal to b. So, just recall how do you solve this equation Ax is equal to b, say where A is an n cross n matrix and x is an n cross 1 vector and b is an n cross 1 vector. If determinant A is different from 0, all right, when matrix A is invertible, A is non-singular, the determinant is different from 0, then in that case you will be able to compute the inverse of this matrix and write down the solution as A inverse B. This is how you have solved some simple matrix equations where A is a 3 cross 3 matrix or 2 by 2 matrix in your previous semesters, or you would have solved them in school. Suppose A is such that it is a very large matrix. In scientific applications, when you solve a certain differential equation using finite difference methods or finite elements method, you would come across a large number of algebraic equations where namely n will be very, very large, and then computation of inverse is going to be a complicated one, and therefore we need to find techniques or develop techniques so that we should be able to compute A inverse numerically. So, in this topic we will develop a number of techniques, namely both direct as well as iterative techniques for solution of matrix equations of the form Ax is equal to B. As I said earlier, because we are numerically obtaining the solutions of these matrix equations, error will be incurred at each step, and we will be focusing on the error analysis in this topic also. And once we do this, then we also consider in this section the eigenvalue problems. We would be determining a scalar lambda and a non-zero vector x such that this matrix equation Ax is equal to lambda x is satisfied. This is called an eigenvalue problem, and we will look at numerical methods for computing the most dominant eigenvalue, because that is very important in many applications. So, our numerical method that we are going to develop will enable us to compute the most dominant eigenvalue lambda and the corresponding non-zero eigenvector x such that Ax is equal to lambda x. We will also be focusing on some results which will give us the location of all the eigenvalues. We will move on to the solution of ordinary differential equations. That is going to be the fifth topic, ordinary differential equations. So, here again, why do we have to solve them numerically? It is a natural question. See, you would have solved in your school a simple first order equation of the form dy by dx is equal to f of x comma y. What does this differential equation tell you? And you would also have solved this equation subject to the condition that y at x naught is equal to y naught. What does this differential equation represent? So, when you solve this equation, what do you end up with? You end up with its solution as y is equal to y of x, which is a smooth curve in the xy plane such that it passes through the point x naught comma y naught, because y at x naught must be y naught. So, it passes through the point x naught comma y naught, and some additional information is given to us. What is it? It tells you that at any point on the curve, say x comma y, its slope is given by f of x comma y, namely the tangent to the curve at x comma y has its slope given by the right hand side f of x comma y. So, you look for a solution which is a smooth curve y equal to y of x, which passes through some point x naught comma y naught which is given to you, and which has its slope or tangent to it at any point x comma y to have slope to be f of x comma y. So, you are looking for such a solution. If suppose f of x comma y is such that it can be represented as a product of two functions, say capital F of x into g of y, and that is dy by dx, then you know you can apply a variable separable technique to solve this equation. if f of x comma y is a homogeneous function of x and y, again you know how to solve the homogeneous equation. If the differential equation is an exact differential equation, you know how to solve it. If it is a linear Lagrange differential equation, say of the form dy by dx plus p of x into y equal to q of x, then again you know how to get an integrating factor, make it exact, and then get the solution of this problem. So, there are special cases where you will be able to analytically solve the first order differential equation. However, if f of x comma y is a nonlinear function of x and y, and you are unable to get the solution of this differential equation analytically, then you need to have some techniques by means of which you should be able to get the solution of this differential equation. So, we would be determining in numerical solution of differential equations this smooth curve in the form of discrete values in the xy plane. We start with the point x naught comma y naught, and we will obtain the value at some x1, say, which is at a distance of say h units from x naught, and then find out what this y1 is. This y1 will be determined in such a way that we know the slope of the tangent to the curve at this point to be f of x naught comma y naught. So, we can approximate, right, the value of y1, for example, by saying that this y1 is determined in such a way that it is the ordinate at the point x1 such that it intersects the straight line passing through the point x naught comma y naught and having slope given by f of x naught comma y naught. And if I drop the ordinate at x1, the point where it intersects is going to give me the y1. So, I have the information about y1. So, I now know what is x1 y1. So, I can compute the slope at that point, which is f of x1 comma y1, and apply the same argument at the point x1 y1 and compute what x2 comma y2 is, and so on, and compute say the point xn comma yn. Once I have information about these points, I can join these points by a smooth curve, and that will give me the solution y is equal to y of x of this differential equation, but I have been able to compute this solution numerically. So, we will develop different methods for computation of solution of such first order differential equations, and applying these techniques and extending them, it is possible to obtain solutions of higher order differential equations. Again, we will focus on how much of error that has been incurred at each step of our computation. So, we will perform the error analysis here also. So, these are some 5 important topics which will enable one to use these techniques and solve some simple problems that arise in scientific applications, which may involve approximation of functions, or approximation of the derivatives of the functions, or solution of algebraic or transcendental equations, or matrix equations, or solution of differential equations. So, these are going to be the topics that we would like to focus on in this course, and as I said, the knowledge for developing these algorithms is not large as far as numerical analysis is concerned, but it is important that one has a strong knowledge about what the background is.